Alright, so up to this point we've talked about addition and subtraction for vectors. Now what about multiplication? So just as with addition and subtraction, we had to take the directionality of the vectors into play. The same thing has to happen with multiplication. So this is where the dot product comes into play. The dot product can be defined. That's not a very good B. As the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle in between them. Okay, so let's look at that for a second. Look at this equation here. So, if cosine, if you remember your unit circle, cosine of theta, when theta is equal to 0, when the two vectors are collinear or parallel, when that happens, cosine of 0 is 1. So when A and B are in the same single dimension, this becomes a single dimension operation. Just a regular multiplication of scalars, just like we're used to, A times B. Now, if theta is equal to 90, so if A is perpendicular here, cosine of 90 is equal to 0. So the dot product will then be equal to 0 at 90. Whenever two vectors are perpendicular, the dot product will be equal to 0. And this will continue on. If A is at 180, cosine at 180 is negative 1, so this will be negative. And then cosine down here at 270 or negative 90, that is also 0. So the whole unit circle applies here. All right, so let's take that knowledge there, and let's apply it here to the three-dimensional Cartesian coordinate system, which we all know and love. All right, let's take the unit vectors of this system, which are I, J, and K. Okay, let's take the dot product of these two vectors, of any of these two vectors. Let's do I dotted with J. Okay, that equals the magnitude of I multiplied by the magnitude of J, which are both just 1 because these are unit vectors, multiplied by the cosine of the angle in between them, and these are perpendicular, so that is 90 degrees. So, remember, unit circle again, cosine of 90 is 0. So the dot product of any of these two vectors, or any two perpendicular vectors, is equal to 0. Okay, so this knowledge here will come in handy when we go to our second definition of the dot product. So the dot product can also be defined as the dot product of all the component parts. So we have AX in the I direction plus AY in the J direction plus AZ in the K direction, dotted with BX in the I direction plus BY in the J direction plus BZ in the K direction. Okay, so let's factor that out. So A dot B is equal to this first term here, AX in the I direction dotted with BX in the I direction plus AX in the I direction dotted with BY in the J direction. Now wait a second. I and J, when dotted together, is equal to 0. So those we aren't going to continue on because these AXI and BYJ are equal to 0. Okay, so now next we have AXI and BZK. And again, K and I are perpendicular to each other. So that's equal to 0. So then we can continue on. AY, that's not a Y. J dotted with BY, J, and then AYJ dotted with BXI. I did the order backwards, but BXI, those two are equal to 0. And then AYJ dotted with BZK is equal to 0. Because remember, two unit vectors, or two vectors that are perpendicular to each other, the dot product is equal to 0. So then we continue on to the last term. I'm sure you can see where this is going. This AZK dotted with these two terms here is equal to 0. So we're only going to include BZK. All right. So now we have a magnitude multiplied by a unit vector on all of these. Okay. Let's simplify this down again. So I dot I, these two unit vectors have the magnitude of 1, and they have the angle in between them is 0, so the cosine is 1. So it's 1 times 1 times 1. So that all just goes away, and this just becomes AX multiplied by BX. And the same thing here. AY multiplied, again, because two unit vectors in the same direction is just equal to 1. BY plus AZ multiplied by BZ. Okay, so this is the other definition of the unit vector. Okay, so then we can combine these two and say that A multiplied by B, these are magnitudes, multiplied by the cosine of the angle in between them is equal to AX multiplied by BX plus AY multiplied by BY plus AZ multiplied by BZ. All right. So the dot product can be used for a myriad of different things in science and engineering. For the purposes of this class, one of the primary functions we'll use the dot product for is to find this angle theta, this guy. So we can then define this, simplify this dot product to be handy to us. We can divide over the A and the B, and then do the arc cosine of both sides to find theta. And so we can define theta as being equal to AX multiplied by BX plus AY, it's not a very good Y, multiplied by BY plus AZ multiplied by BZ, all divided by A, this is the magnitude again, multiplied by B, okay, and then the arc cosine of all of this. That's how you find the angle between two vectors using the dot product. And so this angle tells us the directionality of A relative to B. So another thing the dot product can do, which will be handy for us, is telling us how much of A is in the direction of B. Okay, and this is just using basic trig stuff. So say we have A in that direction, and then we'll just put B right here. Okay, so imagine that A is some force vector, okay? And then B is just some unit vector, magnitude of 1. What the dot product allows us to do is figure out how much of A is along B. Okay? So as an example, to use the dot product here, you would say A dotted with B, remember B in this case is just a unit vector, is equal to A multiplied by B multiplied by the cosine of the angle in between. Okay, so in this example here, B, remember, is a unit vector, so this is equal to 1. So A dot B is A multiplied by the cosine of the angle in between them. And then, so in this case, A will be some value, some number, and cosine of the angle, in this case, will also be some fraction of 1. So that'll be the value of A, the magnitude of A, multiplied by some fraction of 1, and it will give you A along B. And that'll come in handy later on too.